Welcome to homework.
Hey there guys, how's it going? Today we're going to talk about a central limit theorem in stats. So the way I like to start stats problems is by listing out the things that were given in the problem, the theorems that we might use, as well as any sort of formulas that we're going to need. So right off the bat, we are given that there's an average breaking strength, or the mean, is 2,000 pounds. So on average, each of these cables breaks under 2,000 pounds. There's some that can break below 2,000, there's some that can break above. But the average for the population is 2,000 pounds. We're also given that the standard deviation of the population is 100 pounds. So each standard deviation is going to be plus 100 or minus 100 per standard deviation. And then we're given our sample size is 20 cables. So they're going to sample 20 cables at a time and get an average of their breaking strength. We're also given that this problem is assumed to be normally distributed. And that's going to be important when we take a look at our central limit theorem. So now we have all these things. What are we being asked to do? We're being asked to find a sample mean that cuts off the upper 95% of all samples. So we need a sample mean, which in this case we will call m of x, x being our sample. And if we have a sample mean, usually means we're going to need a sample standard deviation. Which in this case we will call standard deviation of x, just so it matches. Alright, so when we need a sample mean and we need a sample standard deviation, and we're given the population, we usually use the central limit theorem over here. Central limit theorem has three different points. The first being that population mean, m, equals the sample mean, mx. Alright, pretty straightforward. So we can come over here. We also see that the sample standard deviation, so SDX, equals the standard deviation of the population divided by the square root of our sample size of 20. All right. The last thing down here is kind of the make or break. All right. Our sample size has to be greater than or equal to 30. Now, you may be saying, well, we can't do this problem then because we have a sample size of 20. And you'd be right if the problem hadn't given us that the population is assumed to be normally distributed. The only reason n has to be greater than or equal to 30 is because you want to ensure that your population is normally distributed. That's how this central limit theorem works best, is when our populations are normally distributed. All right. So because we're given this normally distributed in the problem, we can kind of ignore that our sample is 20. All right. And we can move on and solve the problem as is. So the first thing that we can do right off the bat is fill in our sample mean. Due to the central limit theorem, it is assumed that our sample mean is going to equal our population mean of 2,000 pounds. All right, pretty straightforward. We already have one of our unknowns. The next thing that we need to do is find our sample standard deviation. Now this is going to go ahead and take a little bit of math, but I'm sure we can get it done. All right, so what we're going to do is we're going to start off with our sample standard deviation. Sorry about that. We're going to start off with our sample standard deviation. Okay. Now, over here we see that the formula is our sample standard deviation equals our regular standard deviation, which is 100. And we divide that by the square root of our sample size of 20. All right. So doing some radical math, we multiply it by the square roots of 20 to cancel out that 20 down there and move the radical up top, because we don't like radicals in the denominator of fractions. So doing that is going to get you a mixed radical of 10 over 5, or 10 times the square root of 5, which is going to approximately equal 22.36, and in this case, it'll be in pounds. All right, so now we can come up here and we can go ahead and fill in our standard deviation of 22.36 pounds. All right, so moving on, we're going to go ahead and draw our curve for our samples. All right, so we've got baseline, we've got average, we've got a nice little curve, and I like to draw in my standard deviations just because it helps me visualize. I recommend that you do the same. Usually draw in about 3 on either side to make things easy. And down here is our average, that 2,000 pounds. And each standard deviation will be plus or minus this 22.36. So we'll say plus or minus 22.36. Perfect. So now we can actually go ahead and start solving for that upper 95%. All right, we want an upper 95%. So we already know that this right here is 50%, right? Because this whole curve is 100% of our 20 size samples. This right here is our 50%, right? And we know that each of these each standard deviation has a percentage assigned to it. So this one right here would be 34. Same thing with this. This right here is 13.5 approximately. We have 2% and 0.5%. All right, so all together that'd be 50%. We are asked to find 95% in the upper 95%. So if we add on another 34, we're going to get 84. Not quite enough. If we try to add 13.5 onto that using this standard deviation, it's a little too much. So what we need is something that's going to be probably right about in here to make the rest of this 95%. Okay. So we want upper 95%. All right. And while we're here, let's go ahead and fill in this down here as the lower 5%. So we are looking for a value. We're looking for a value, this value right here, that cuts off this 95% because we only really want this bottom 5%. We want to cut all this off. Okay, so how do we find this? Well, when dealing with percentages, we have to look at our Z tables. Okay, so if we come over here, we have a Z table right here. Z tables are made up of percentages and their corresponding values. So Z is the approximate of a standard deviation. Okay, so 0 right here is 0.5 because 0.5 is going to be our mean. So 0, 0 is going to be our mean. So in this case, it would be 2,000, right? So we also need our our z value, right? We need our formula for our z value. So we have z equals x minus mean, and in this case it'll be our sample mean, divided by the standard deviation of our mean, or of our sample, okay? So that's our formula right there. That's the formula that we're going to be using. And you may be thinking, well, how the heck do I get a z value? All right, so let's go back here. We have 5% right here, right? And 5% can be written as 0.05. That is 5%. All right, and 95% would be 0.95. All right. So when we look at z-tables, we have to think in terms of the left-hand side of the curve. All right, so in our case, the left-hand side of the curve is the 5%. So we don't really need this 95%. We just need the 0.05. We just need the 0.05. So when we're looking at this, we've got to find a percentage in these numbers. We have to find our percentage in these numbers, right? The closest we can get. So the closest we can get to 0.05 is actually going to be right in here. It's going to be these two numbers right here, all right? Because they're both equally as far from 0.05. So we'll start with this number right here, negative 1.6, okay? So we'll say z equals negative 1.6. All right, so we'll travel on down over here to these two values, and 0.05 is probably somewhere right in the middle. All right, so if we come up here, we take a look and we're given our values for that third number. And ours is right in between 0.04 and 0.05. So what we can call it is 1.645. Perfect. And now we can keep going with our formula. So this number is going to be equal to x, which is the value that we're trying to find that's cutting off the upper 95%, minus our mean. So our mean was that 2,000 pounds. And we're going to divide it by the sample standard deviation. Make sure you use the sample standard deviation and not the population. It's very, very important to use the sample standard deviation because we're looking at our sample percentages. We're not looking at our population percentage. We're looking at samples. So we got to use the sample mean and the sample standard deviation of 22.36 pounds. All right, so when we go ahead and solve this out, we multiply over, and we get that. We get negative 36.78 equals x minus 2,000. And when we add our 2,000 over, we get x equals 1,963.22. And in this case, we have our unit as pounds. All right, so if we come back over here to our curve, we were looking for this x value right here, right? That x is this x, which is that 1,963.22 pounds. So this value right here is going to cut off the upper 95% of all 20 size samples pounds, or 20 size samples average.